So let's talk about what's become a very popular technique in generative AI, Retrieval Augmented Generation, or RAG for short, or as I like to call it, cheat to win. Let me talk about why. So RAG is kind of like an open book exam for large language models for your generative AI models, and I didn't make that up. They've been calling it that from the get-go. The idea is that you're going to query some external database for the answers and give that to your large learning model as part of the prompt or part of the process of generating its response. So in a way, it's cheating. You're looking up the correct answer from some external data source and injecting that into the generation of the actual response. So you're not really relying on the underlying model itself, except for really just how to reword what you've given it for information, right? So let's take a look at this example on the right here. Let's say I'm asking my chatbot, what did the president say in his speech yesterday? Well, we all know that most large learning models like GPT and whatnot have only been trained up to a certain date in the past, right? So they typically don't have up-to-the-date knowledge. Let's imagine, though, that we pass that into RAG, like my little picture of a RAG there. So let's say that it goes off to a database that's kept updated every day of the latest news articles. I could query that database and say, hey, do you have any articles about the president giving a speech yesterday on a given date? Maybe it comes back with some sort of a match that's relevant to those parameters to that query. And we get that back and we just stick that in the query before we pass it on to the actual generative AI model. So then we can sort of frame that query, sort of reformat it using a template and say something like, what did the president say in his speech yesterday? Consider the text of the following news article in your response, and then paste in the text that you got back from the database. And if you phrase that the right way, ChatGPT or whatever you're using can use that to generate a response that takes that information into account. So it's a way of incorporating external data that may be more up-to-date or even proprietary that you didn't have before, but it's kind of cheating. You're kind of making a glorified search engine here, right? So let's talk about the pros and cons of RAG. What's it good at, and what are some of the downsides of it? Well, the big upside, the pro column here, is that it's faster and cheaper for incorporating new or proprietary information compared to fine-tuning. So we looked at fine-tuning earlier and had an example of that. It took hours and hours and hours for that to happen, right? So it was also pretty expensive. In comparison, though, using RAG can cost less than a penny. We're going to do an example at the end of this lecture, actually, where we do that same thing where we did with fine-tuning to recreate the character of Data from Star Trek, but we're going to do it using RAG instead of fine-tuning. And literally, it costs less than a cent to do it. So economically, it's very attractive. And if you're a company trying to implement this stuff and push out some innovative AI model that takes your own company's information into account, it's a very tempting way to go about it. Updating information is simple. You just have to update the database that you're pulling that information from, right? So you don't have to go back and retrain anything. You just update your database and that gets injected into the system as it's generating responses. Now, the real benefit of RAG that's promoted most widely is that it's a potential solution to the hallucination problem. So when you go and talk to an AI enthusiast and you say, yeah, generative AI is great, but it lies a lot, they say, oh, but we have RAG. You can use that to actually inject trusted data into your responses and prevent that problem of it telling you incorrect information. Well, yes and no. So if you are going to ask it about something that it wasn't trained on, a good model will just say, hey, I don't know the answer. You know, you're asking me about something that happened after my training cutoff, right? But sometimes it will just make stuff up. And if you're giving it a source of information that's better than making stuff up, maybe on the whole that's better. So, okay, yes. It can help, but it's not a solution to the problem. It's not going to completely prevent hallucinations wholesale. If your boss says, I want AI search, this is a really easy way to do it, because basically you're just taking a search engine and wrapping it with AI, right? That's how RAG works. You're going off and querying a database, searching a database for some answer, and feeding it to a generative language model to give it a more human response, right? Also, keep in mind that technically you're not training a model with this data with RAG. So if you're using some sort of proprietary information where there might be restrictions about how you use it, you can say with a straight face that you're not actually using that data to train an AI model. And well, there might be political consequences to doing that, right? On the con side, though, you have now created the world's most complicated search engine, right? You've taken this very straightforward search to a database, which we've been able to do for decades, right? And you've wrapped it with this incredibly complicated generative AI system. Why? You know, maybe you don't even need to do that. Maybe you're better off just giving those search results right back to you, right? I've seen one example, for example, where they use RAG to produce product recommendations. And they do that by querying this big graph database for getting recommendations that were pre-computed using traditional methods. And all they're doing with the AI part of it is just rephrasing that into natural language. Why? Just present back the product recommendations as is. You don't need to take on that extra complexity and that extra expense necessarily. So do ask yourself if you're overcomplicating things by using RAG. Also, it's going to be very sensitive to the prompt template that you use to incorporate your data. So the way you ask it to incorporate that data can really influence the results that you get. So just based on the wording, when I was playing around with it, if I worded things the wrong way, it just parroted back those search results exactly verbatim as is. It didn't even try to rephrase them or incorporate information from the underlying model into the response. So you do have to experiment with how you're phrasing your prompt to say, take this data into account. By the way, that's not the only way to do it. We'll talk about that in a minute. There are some slightly more principled ways of handling RAG than just modifying the prompt. But either way, you're going to need a prompt to tell the underlying model how to use this data. And because of that, it's non-deterministic. So let's say that there is a new version of the model that rolls out that was trained on different data or trained in a different way. Maybe the way it reacts to that prompt will change over time as a result. That's kind of a scary thing, right? Like if the underlying model changes, the results that you might get from RAG could just stop working entirely for all you know. And it can still hallucinate. Like I said, it's not a general solution to the hallucination problem. It's going to be very dependent on the relevancy of the information you're retrieving, right? So if your retrieval from that database is not giving you highly relevant results, it could still result in hallucinations or giving you misinformation, right? It's only going to be as good as that data that you're pulling from that retrieval stage. So keep that in mind. Again, it's not a panacea. It's not a complete answer to the hallucination problem. So let's take a look at a specific example here. Let's say I want to build a chatbot that's really good at answering questions from the TV game show Jeopardy. So if you remember Jeopardy, the idea is that you give it an answer and you have to give the question, right? So in this case, the answer is, in 1986, Mexico scored as the first country to host this international sports competition twice. So how could I use RAG to go answer that if that's not something that the underlying GPT or whatever it is knows about? Well, that's where our retriever module comes in. So we pass that raw query into our query encoder. Its job is to expand on that query and incorporate data from our external retrieval. So let's say I have a database of every Jeopardy answer and question that's out there from all time. I can query that database for that answer and come back with a list of the most relevant questions that are associated with that answer, right? So I'm going to get back a list of documents sorted by relevance for that query. And I can then incorporate those into the query itself and rephrase that query to say, in 1986, Mexico scored as the first country to host this international sports competition twice. Please take into account the following known question: what is the World Cup? And that gets passed into the generator, which just gives you back a nice natural language response that basically says, what is the World Cup? So that's an example of RAG. Again, it's pretty simple to wrap your head around. All we're doing is querying some external database of some sort, taking the results and working that into the query before we pass it on into the generator. That's it. So basically, we're just handing the generator potential answers from an external database. We're giving it the answers. That's why I call it akin to an open book exam. So how do you pick a database? There's many ways of going about that. What are you going to query in that retrieval stage? Well, you can use whatever's appropriate for the type of data that you're retrieving. So I talked earlier about that example of retrieving product recommendations. For that, maybe a graph database is the most appropriate choice, something like Neo4j. Or if you're just doing traditional text search, you can just use something like Elasticsearch that will give you back relevant text matches based on whatever you're searching for, just using TF-IDF, term frequency and inverse document frequency. We talked about that earlier in the course, or anything along those lines. You can also often sort of manipulate these search engines into being something else, but I'll talk about that in a bit. Another approach, though, is instead of just doing a prompt injection like that, you can also do something a little bit more principled. So you can use the Tools API and the OpenAI API, for example, and use that to try to get GPT to provide structured queries to inject into your actual modified query, right? So they have an example online called RAG with a graph database. And that's one example of how to do this. There's a link here if you want to go check it out. But that's what this stuff on the right here is doing. So basically, we start off by saying, okay, chatbot, okay, OpenAI, here is some general rules on how to create structured data requests from a given question that I see. So if I give it this really long system prompt that says, look for these kinds of words, look for these types of things in the question, and I want you to structure it in this way, you can actually get it to actually create structured data like this. So for example, if someone says which pink items are suitable for children, it might be able to automatically produce this structured little JSON snippet that says color pink, age group children. So if you give it enough specific instructions, it can actually structure that for you. And then if you're using the Tools API, which we talked about a little bit earlier in OpenAI, for example, you could actually have that passed back into a function that OpenAI uses when generating the actual response. So it's a little bit more complicated than just modifying the prompt, a little bit more structured, but still you're depending on that system query to make sure that it knows how to construct this structured data accurately. It's a little bit more complicated, not necessarily better. However, for some reason, when you go and look for examples of retrieval augmented generation online, usually you find people using something called a vector database. So let's talk about what a vector database is. Now, before we talk about vector databases, let's first review what embeddings are. And you'll see why this is relevant. An embedding is just a big vector associated with your data, right? So that's why we're talking about vector databases here. Embeddings are vectors. So you can think of an embedding as a point in this multi-dimensional space. And in practice, that's usually hundreds or even thousands of dimensions, where everything is sort of positioned based on its similarity to other things. So embedding vectors, which are, hundreds or thousands of dimensions in size, are computed such that items that are similar to each other are close to each other within that higher dimensional space. So to let you wrap your head around it again, imagine that we have a two-dimensional embedding here, where we just have X and Y axes, because we can visualize that on a screen here. Maybe the words potato and rhubarb are going to be close together in those spaces, and that embedding vector would just be the vector from the origin to where those are in this space. However, for example, stuff about science fiction like the Starship Enterprise, Spaceballs, the Orville, maybe those are all clustered somewhere else, right? But they're still going to be close together because they have a certain similarity to each other, right? Now, the good thing is that embeddings can be very easily computed if you're doing machine learning language stuff already, right? So you already need to deal with embeddings if you're creating any sort of deep learning natural language model. So often you can just use existing tools at hand to compute these embeddings and make it easy. So OpenAI, for example, has an embeddings API that we looked at earlier, and we can use that to compute a bunch of embeddings all together at once at extremely low cost and quite quickly as well. So once you have these embedding vectors for everything, you just got to stick them somewhere. So let's put them in a vector database, shall we? All a vector database does is store your data alongside their computed embedding vectors. And that gives you a very easy way to search for things that are similar to the thing that you are searching for. Again, you can leverage the same embedding system that you might already have for your larger system, which makes things a little bit easier. Retrieval is going to be take a couple of steps. So if there's something you want to search for, find something similar for, first you need to compute an embedding vector for it. And then you will query the vector database for the top items that are close to that vector. So basically we're doing k nearest neighbor in this multi-dimensional embedding space to get back the top n most similar things. We call that vector search. That's all it is. It sounds fancy, and honestly, I think a lot of this terminology and fancy talk is just to help sort of legitimize what's kind of cheating, like I talked about, but it works, so I'm not going to criticize it too much. Now, there are different vector databases out there you can use. Like I mentioned briefly, you can coerce a lot of existing databases to do vector search that weren't necessarily designed for it originally. So there are ways of using Elasticsearch, traditional SQL relational databases, Neptune, Redis, MongoDB, Cassandra, many others to do embedding, to do vector searches just by structuring things the right way. But there's also purpose-built vector databases out there as well. On the commercial web service side, we have things like Pinecone and Weaviate. And if you go search for examples of using RAG online, most of them use those services. I kind of think they might be getting a kickback from them. There's also open source solutions as well, though, like Chroma, Marco, Vespa, Qdrant, LanceDB, Milvus, and more recently VectorDB. That's a very simple little Python module that we're going to use in our example shortly. So let's talk about that example. Let's say that I want to create data from Star Trek, but this time instead of using fine-tuning and actually building up a fine-tuned model that really sort of mimics the brain of data, if you will, this time we're going to cheat and we're just going to use RAG. So how might that work? Let's say a user types in a prompt, data, tell me about your daughter Lal. So how might that work with RAG? So first we need to compute an embedding vector for that query. Data, tell me about your daughter Lal. And we'll get some sort of, multi-dimensional vector that says where this sits in our embedding space. We can then do a vector search in our vector database that's been pre-populated with everything the data ever said before, right? So just like we did before with the fine-tuning API, we have a document that we built up of every line of dialogue that data ever said. And we can stuff that into a vector database offline. That involves looking up, in batch manner, every embedding vector that's associated with every script line. So offline, I have this script that looks at everything data ever said, computes the embedding vector for that line, and stuffs it in this vector database. And that's faster than you might think and cheaper than you might think too. Again, when I did this for real, using all 200 episodes or whatever it is, it still cost me less than 1 cent in US dollars to do all of that, multiple times, mind you. So very fast and very inexpensive to populate that data. But when we do that vector search for our query, data tell me about your daughter Lal, it's going to give me back the top however many similar lines I want to see, right? Maybe it's the top 10, whatever it is. It will give me back the most similar dialogue lines that talk about Data's daughter Lal. And how you make that relevance work, again, is key to the performance of a RAG system. So that quality of those results, the relevancy that you're getting back at this stage, is really going to influence the quality of the system as a whole. So now I can take those top similar lines and just embed them into the actual modified query that I'm going to send along to the actual model. So I might rephrase that original query to say, you are Commander Data from Star Trek. How might Data respond to the question, Data, tell me about your daughter Lal, taking into account the following related lines from Data? And then I would proceed to paste in the list of the top 10 similar lines that I found from my vector database there. And when I feed that in turn into the chat completions API for OpenAI or whatever model you're using, I will get back a response that hopefully takes those external results into account. And we can go and try it out. So again, that final prompt that we're creating in RAG is going to be a combination of the original query, the prompt template that we're using, and any relevant data that we extracted from the retrieval stage of RAG. That's all there is to it, folks. So let's go and actually build this thing now and see if it works.